So I will introduce the first speaker. So it's Katherine Joy, and she's going to be telling us about the potential for the age of the South Pole Aitken Basin being preserved in lunar meteorite. So Katie, when you're ready, take it away.
It's very exciting to be back talking about the moon in a conference again, and I'm going to talk today about some collaborative work we've been doing between different research groups in the UK and China. And most of this work was done by our visiting PhD student Nian Wang, who visited Manchester pre-COVID for a 6-month visit. So I'm going to talk about lots of different data sets we have from one lunar meteorite, and then make the case why this meteorite potentially preserves the age of the South Pole Aitken Basin. So to give you a little bit of context, we'll start by looking at a picture of the moon before we get to our lunar sample itself. And just to remind you of the locations where we have samples that have been returned by the Apollo missions, by the Russian lunar missions, and then most recently from the Chinese Chang'e 5 mission. So all of these near side of the moon, all of them from the equators. Currently, we don't have a sample return mission that's visited the far side of the moon. But why this is really important to consider is we really need global sampling of all the different geological terrains to piece together the moon's geological evolution from its formation through to crustal formation, through to impact history and subsequent volcanic history as well. So when we look at the moon in different data sets, we can start to understand the number, the size and the magnitude of the different impact basins that cover the lunar surface. So this is an LRO LOLA topography map, where we can start to pick out the size and extent of some of the big basins. And to draw your attention to the basin I'm going to talk about today, this is the largest basin on the moon, 2,500 kilometers in diameter, about 13 kilometers deep from rim down to the bottom. And in the topography data sets, it's an incredibly obvious feature to see, located on the far side, southern regions of the lunar highlands. We can look at other data sets as well. So this is a Thorium Map collected by the Lunar Prospector data set, where we can now see the moon is divided up into different geochemical terrains, where the near side of the moon dominated by the Prosolarum creep terrain, an area of high thorium, high radioactive elements associated with creep, which is related to the late stage dregs of the lunar magma ocean. But the far side South Pole Aitken Basin, you see, has a slight enhanced thorium abundance as well, although is notably different from the near side. So we have lots of questions probing why the far side of the moon is different from the near side, and in particular why we don't see such a high thorium abundance in this large impact basin that's been exposed. So I'm going to refer to several different basins in the latter part of this talk, so I'll try and orient you as much as possible. But just to reiterate the fact, SPA is the focus of this particular talk, and there's going to be a flash talk and a poster later on in this session about the geology of SPA, which I don't claim to be an expert in, so I'm going to point you to go and see the research presented there. But SPA, enormous size, it's been overprinted by numerous younger basins such as Schrödinger and Apollo. We have outcrops of mare basalt, so this is volcanic products sitting at the lunar surface. And we have visited the South Pole Aitken Basin. The Chang'e 4 mission touched down in the von Karman crater. So although it didn't conduct sample return, we do have an indication of the chemistry of some of the samples on the far side. But SPA is really key to address some fundamental questions we have about the moon, including the age of the basin itself. We think it's the oldest basin on the moon, but the age of that is quite uncertain. That's one of the big constraints we want to put on. And we want to understand whether the giant impact that formed the South Pole Aitken Basin was able to actually melt the crust enough so that it could differentiate into different types of constituent rocks, and lots of questions about the far side lunar crust. So this is a great site that we have to go and visit someday. But short of that, what can we do? Well, the best way we can sample SPA is through the hope that we have some lunar meteorites that have been sampled from there. So although we've not gone with any of our sample return missions, we estimate that because SPA represents about 16% area coverage of the moon, we should have in our lunar meteorite collection about 50 to 80 meteorites that have been launched from this landing site. And so the question becomes then is which ones can we potentially associate with SPA, and how do we do that when we haven't got any rocks from this region of the moon to compare with? So this turns our attention to Lunar Meteorite 2995, which was found in Northwest Africa. It's been proposed by two other research groups before to be chemically similar in terms of its bulk chemistry to the types of remote sensing geochemical data sets we have collected from the moon, and specifically to the regions within the South Pole Aitken Basin. So we targeted this rock as a really good sample to go and test some of these ideas to say, well, A, do we think it's come from SPA? And I'll get back to that later on in the talk. And then if we can convince ourselves that this is a meteorite from South Pole Aitken Basin, what types of records, chronology records and geochemistry records are preserved within it that could tell us about these key questions we have about the basin? So this is a mugshot of our meteorite. It's made up of lots of different rock fragments that have been consolidated together into a matrix. And so we go on what we call a class provenance study, where we try and pick apart all the different classes in this meteorite to work out what lithologies they're related to, and then how can this relate to key processes. We know this sample was once a soil, so it actually formed at the surface of the moon because we found evidence in some of the samples that have been looked at before of soil-like components. So we call this sample a regolith breccia. And that's really important because it allows us to make this key comparison between the chemistry of the soil of the South Pole Aitken Basin at the present day and through the remote sensing data sets and the chemistry of this meteorite. So what did we do? Well, we took a relatively small slice of this sample, we polished it up, we looked at it under an optical microscope, and this is an optical image. You can see again this sort of white class distributed throughout the meteorite in a relatively dark coloured matrix. We undertake a scanning electron microscope mapping of the sample to identify the different class types. This is a backscatter electron image where again you can start to pick out some brighter coloured class, and these relate to samples that are richer in iron. They represent rocks that are pyroxene rich in nature, and then we have some darker material which is actually silica quartz, which is quite unusual for lunar samples. We then do some chemical mapping to look at the distribution of the chemical elements in these the different class components, and work out which ones we think we should go and pay closer attention to. And we can also identify through this chemical mapping mineral phases that we can do dating work on. We've looked at this sample in other ways as well. So we've conducted cardoluminescence mapping of the sample as a whole, and then we've looked at specific mineral phases in a bit more detail to try and understand how different minerals within this sample have been altered, have their crystalline structures changed by shock pressures, which allows us to probe this sample's impact shock history as well. So when we look at things in a little bit more detail, to introduce you to some of the key class types we see in this sample, when we pick things apart, here's some pictures in backscatter electron imagery at the bottom of the key class in the sample, which represent a type of rock that we call a quartz Monza gabbro. So this means rocks that are rich in quartz, they have pyroxenes, and they have relatively alkali-rich feldspars. So quite unusual for most of the rocks we see on the moon. And indeed, this rock in the middle here represents what we call a granophyric class. It's rich in silica and K feldspar. Not much of the moon is granitic in nature, so again, quite an unusual type of rock. When we carried out electron microprobe analysis to look at the rock mineral chemistry, we can see that some of these class are fairly diverse in nature. They represent potentially relatable but slightly different types of parent mount chemistries. And we think that although these rocks represent different classes that are being broken up, we think that they're actually related to the same rock type that was formed at depth, at shallow magma chamber-like conditions in the moon. Now, from studies of similar rocks in the Apollo collection, there's actually quite a big argument about what depth in the moon these types of rocks are formed. We have estimates all the way from relatively shallow magma chambers, about 1 kilometre deep, down to depths at the near base of the lunar crust, depending on which studies you look at. So they're a rock suite which is well worth looking at in a lot more detail. And indeed, my colleague John Pennant-Fisher is actually doing some analyses of Apollo equivalents of these types of samples to understand some of these issues in a little bit more detail. So we hope to talk about that later on next year. But looking back at this type of meteorite in a bit more depth, we turn our attention now to the dateable phases in this meteorite. So we were able to identify a mixture of apatites, merolites and zircons, which are all minerals that we can date using the In-Situ uranium-lead dating system. And we've looked at these different phases in different ways. We've looked at them to understand their textures. We've looked at them in cardoluminescence to understand how they've been altered through shock or other processes. The challenges we've got with many of these grains is that they're not actually associated with a particular rock type. They kind of represent random mineral grains that we find in the matrix, with a couple of very important exceptions, which seem to be associated with mineral fragments that we think have come from these quartz monogabbro parent rocks. So we think that many of these zircons and apatites have been liberated from this specific type of evolved parent lithology. When we look at them in a bit more detail, we see that there are zones that are relatively unmodified, and when we look in Raman spectra, these represent mineral fragments that have not been altered from their typical crystal patterns that we would normally expect to see under Raman. But when we look at other zones within these minerals, they've been heavily altered, and in fact they've become quite amorphous, so they've lost their crystalline structure, which is important because it tells us that potentially these minerals have been highly shocked, highly changed through applying high shock pressures. And we're currently doing a little bit more work to see if we can identify specific shock polymorphs in these types of mineral phases. We've dated the apatites and the zircons using slightly different analytical setups. This work was done in Beijing on their SIMS instrument. We've conducted lead-lead dating of the zircon phases and uranium-lead dating of some of the apatites. And the apatites are highly disturbed. We see highly discordant ages, which tells us that they've been partially reset by either a high shock or temperature processes. But when we look at these two different minerals, they give us essentially the same age, which is important because it tells us that they record the same type of geological event in both of these different types of minerals, which can be affected by shock or high temperature resetting, normally in slightly different ways. So it tells us that whatever has occurred with these types of minerals in a sample represents quite a large event. We're trying to pick this apart, but we can ask the question, does this event represent a magmatic event? So the crystallization age of these quartz monogabbros were kind of within the moon when they first formed, or does it represent a large-scale impact later shock resetting age? And we would argue that actually we think that because this is that the minerals indicate the fact they've been shocked, they have changed in terms of their mineral chemistry, their crystallinity, and also their resetting age. We think that is most likely to represent a common large-scale impact resetting age at the age of 4.32 to 4.3 billion years ago. So that's our interpretation of the age data. And that's the age that I'll come now to talk about why we think we ascribe to SPA. I can see Josh popping up in the picture. He's showing me his grumpy face. I'll try and quicken up the argument. Thank you, Josh. So how do we associate this with SPA? Well, what we do is we take the rock's bulk chemistry, which is indicated down the bottom of this plot. We combine it with the chemistry data from the Lunar Reconnaissance Orbiter spacecraft, and we apply statistical analysis where we bring in not only the chemistry data from the elemental maps from the remote sensing missions, but we fold in the data uncertainties, which is not what previous people have done when they've done these types of analyses. And when we do this activity, this is a map now where I'm showing you a colour indices of where this rock most likely has come from on the moon, where the blue colours up to the red colours indicate the likely sites on the moon this meteorite has been liberated from, so it's been launched off before it came to Earth. And we can see that there are the brightest pixels associated with the South Pole Aitken basin, but also some areas up to the north of Serenitatis and Chrysium and associated with Nectaris as well. So what we need to do is we need to combine the age data with the chemistry data to try and address which basin this meteorite has most likely been launched from. And when we do that, so we show in this column here the ages that have been proposed for these core impact basins, all the way through from the Orientale Basin up to the oldest, the South Pole Aitken Basin. And when we combine our analysis of the chemical match to the age data, the best match for both of these scenarios is that's matched to the South Pole Aitken Basin that has been investigated by our crater counting colleagues, counted places within SPA. So we're arguing that this evidence matches up together to represent the South Pole Aitken Basin age. I'll finally wrap up by just saying, why is this significant? Well, the SPA is a key stratigraphic marker when we're thinking about the cratering chronology of the moon. This is the types of topics that Carolyn talked about yesterday. And if we can place the age of SPA at this point of 4.32 billion years old, this helps to tie down our understanding of the basin forming epoch on the moon, and it also potentially helps us to investigate and calibrate that impact cratering record, which tells us all sorts of interesting things about the early bombardment history of the moon. However, I'm going to acknowledge just before Josh really does show me his significantly grumpy face, is the fact that actually really, although this meteorite we think is an incredibly useful record, What we really need is sample return from SPA. And that's exactly what's going to happen next year with the Chang'e 7 mission. We're going to get rocks back, which we'll be able to analyse in the labs to test the hypothesis we're putting forward that SPA is 4.32 billion years old, but also to investigate all sorts of other interesting questions about the nature of the geochemistry of the rocks on the far side of the moon, and to question whether we have lower crustal rocks that have been exposed by SPA or not. So I'll leave it there. Thanks, Josh. I'm happy to take questions in the chat if I've run out of time.
Yeah, I was going to say we probably need to move on, but if there are burning questions, post them in the chat. We'll see if we have a chance to address them later.